I would like to start by thanking the organizers for inviting me. I'm very pleased to be here after a lovely long visit in 2010. And well, this is the last talk, so it will be a very light talk, and thanks for coming. I will talk about the result on the support theorem. Now it's fine. About the support theorem for the stochastic wave equation in dimension 3, and this is joint work with a student of mine, Francisco Delgado. So the objective is to prove a characterization of the topological support for the law of the solution to a stochastic wave equation in a spatial dimension 3. And maybe let me start by giving the definition of the support that is not known by everybody. So given a random vector x, which takes values on say to Polish space, for example, topological space, the topological support is the smallest closed set F, such that the law of x gives a positive measure. So then, if you look at this definition, you see that there are three types or three ingredients which play a very important role. One is, so what type of solution are we considering for the equation? And I will consider random field solution. So the second one is what topology. So when I say a random field solution, so that means that I am fixing somehow this M. So then second one is what topology. And here I will consider the topology given by the Hölder norm and the method. And the method will be that it's mostly based on the use of approximations. So here you have several motivations to study support theorems. So in the context of these workshops, since we mainly are dealing with stochastic partial differential equations, so this is the study of irreducibility, which leads to uniqueness of invariant measure. Okay, I have not applied support theorems to that, but this may be used. So a second motivation, which is quite recent, came to my mind by listening to lectures by Ramakant on his functional calculus, jointly with Fournier. So they study functional Kolmogorov equations, and in most of the hypotheses are based on properties and characterization of the support, which actually they don't have in most of the cases. So it's worthy to explore. And I suppose that for most of us mathematicians, curiosity is also a very good motivation. Okay, as I said, the main ingredient will be approximation. And so there will be approximation in probability and in the Hölder norm of a stochastic wave equation that I will just describe now. And these approximations are done using smoothing, smooth versions of the driving noise. So a sort of infinite dimensional version of Wong and Sakai theorem. So if you are interested in the subject for the method, the abstract formulation of the method was given in a quite old paper by Aida Kushok and Struck in the framework of an abstract linear space that actually I will use here. And then this method was used for SPDEs in several papers, jointly with Annie, with Vlad, with Jones, etc., etc. So there are many papers. And the background on the stochastic wave equation I will use is given mainly in the paper of Dalang in Electronic Journal of Probability, the joint paper with Dalang in the memoirs, and also equivalence of stochastic integrals I will use are proved in this recent paper with Luis Cerdañons. So the work, the plan of the work is to split the analysis into two parts. In the first, first consider the case where the initial conditions are 0, and second case, non-null initial condition. So here in this talk, I will only deal with the first case, vanishing initial conditions. So then you can wonder why such a distinction, and so the reason is that I will use a noise which is especially stationary, and then that means that if the initial conditions are 0, then the solution is also stationary, and this property is very important in some proofs, which and the extension in the non-stationary case needs other ideas. So proofs are different, although the method is exactly the same. So the description of the equation, I am not going to insist very much on this. This is the equation that was also considered in the lecture by Robert. So this is the stochastic wave equation with nonlinear terms and sigma and b. The initial conditions are given in that way, and the noise m is a Gaussian process that, if you would like just to have an idea of what it is Gaussian, as I said, 0 mean, and the covariance is given by this formula. So that means that it's white in time. This delta stands for the delta direct measure, and f is some function. So that means that there is a correlation in a space, and the correlation is given by this function f. If you would like to have more insight, so this is the precise definition of the noise, where the covariance is given in its spectral form, like that. Script f is the Fourier transform, and mu is the spectral covariance measure. So that means that the relation between f and mu is given like that. So f is the Fourier transform of mu. Okay, but just to have an idea, so this is the noise we are considering. Okay, so then the formulation I will use of the equation is like that. So it's mild formulation, and the choice I make for the stochastic integral is what is in red. So here now Wj is a sequence of independent standard Brownian motions. Okay, so this is like an Ito integral, and here capital H is a Hilbert space naturally related with the covariance structure of the noise, as Robert also explained in his lecture. And we are interested in random field solutions to the equation. Okay, and G is the fundamental solution to the wave equation. So this is the form I will consider. So then the background for this equation, well, I need existence and uniqueness of solution, a result on existence and uniqueness. So as I said, I am considering vanishing initial conditions. So there is a result in the paper by Dalang I mentioned before, and also in this more recent paper, which gives existence and uniqueness of random field solution to this equation here. And the solution satisfies some properties. For example, it's continuous in L2, and what is maybe more relevant here is that it's bounded in LP for any P. Okay, so now let me move to the support theorem. So here we are considering the Hölder norm. So just let me introduce some notation. So I will denote by this notation the usual Hölder norm for functions which depends on time and in a space. So for time, I consider a fixed interval t0, t may be 0, but can be greater than 0 also, and k is a compact set of R3. Okay, so this is the usual notation for the Hölder norm, and I will also denote by C rho as usually also the space of real functions such that this norm is finite. And then under more general conditions than the ones I am using here, so it's not necessary to have vanishing initial conditions, we have proved with Robert that for some class of covariances, the sample paths of the random field solution, the sample paths are in this space, okay, for a range, so they are Hölder continuous for a range of rho in this interval, where beta is, so I am using, no, if I said, yeah. So I am using, haven't said that, sorry. So I am considering the function f is a Riesz kernel of order beta. Okay, I forget to write it here. So this is the beta which appears here. Okay, so this is for the Hölder continuity. These are known results. And now, what about what is the statement? So the statement is here. So it says that if we consider the random field solution to the wave equation, and we fix a rho in this range, okay, so then the topological support of the law of U in the space of Hölder continuous functions is the closure in the norm of this space of a set of functions phi h which are constructed as follows. So now remember that I said that H is this space naturally associated with the spatial covariance. So let's complicate a little bit more this space and consider L2 of 0t taking values on H. So this is now the reproducing kernel Hilbert space, okay? And then for each H, you consider this evolution equation. So this evolution equation, so this is deterministic, and the idea here is that we have replaced in the wave equation, we have replaced the term, so initial conditions are 0, we have replaced the term with the stochastic integral by something which looks very similar, but we have replaced the sequence of Brownian motions by an element H which lives in this space, okay? So this is the description, which is very natural if one knows the other support theorems concerning parabolic and hyperbolic problems. So this is the result. So now how to prove this result? So I will briefly recall this method based on approximations, but for this specific case here. Okay. So we'll prove the two inclusions. So to get this inclusion here, which is one of the inclusions to be proved, we notice that in fact the equation I mentioned before, I will refer to this equation like as the skeleton of the equation. Okay, I will call that the skeleton. So it turns out, as you see, this skeleton in fact gives rise to a functional or function mapping defined on the Hilbert space HT, and it can be proved that it takes also values on the space of Hölder continuous functions. Okay, so then assume that we are able to find a sequence of random variables taking values on this space, such that the corresponding skeleton. So when you replace H by this Wn, okay, which takes values on HT, okay, so then this sequence converges to U, to the solution of your equation. But the convergence is in probability, as you see here, and in the rho Hölder norm. Okay, so then in that case, as in the classical result by Strucken-Baradan, and based on the characterization of weak convergence called Portmanteau's theorem, it's easy to prove that you have this inclusion. So this is exactly the same method as for diffusions. This is not the same method as for diffusion. So in order to prove the other inclusion, the opposite inclusion, so here it can be proved as follows. So now let's assume, let's fix H, an element of the Hilbert space, and let's assume that there exists a sequence of transformations of the probability space such that the sequence of transformations are absolutely continuous. Okay. So then assume also that well, if you fix the skeleton for this H, phi H, and you replace omega, but TNH of omega, the corresponding wave equation, sequence of wave equations, converge also in probability and in the Hölder norm to 0. Okay? So, sorry, well, this sequence converges to the skeleton in probability and with respect to the Hölder norm. Then, using Girsano's theorem, one can prove the other inclusion. Okay? So this is the method. So then you see that in both cases there are some convergences to be proved. So now, what is a good choice for the first convergence? What is the good choice for Wn, and what is the good choice for these transformations, or possible choice at least? I don't know if it's good. So for the sequence of omega n, this is also very natural. So what you do is, so remember that you have a sequence of standard and independent Brownian motions. Okay. So then first you project. So that means that you fix n and you just kill Brownian motions of index greater than n. And for those indices which are less than n, so this is what I am saying here, we consider approximations of the Brownian motion based on linear interpolations. Okay, the only little difference here, so this is the derivative of the approximation. Okay, the only difference here is that instead of putting here 2 to the power n, I allow myself some flexibility and introduce a parameter zeta 1, which actually in the proofs play a quite relevant role. Okay, but otherwise, so this is the approximation we consider, and so this can be viewed. So this approximation can be viewed as an approximation of the underlying noise. So this is the idea. So as for the transformation, so we put this in the rigorous setting, considering the abstract Wiener space associated with the sequence of independent Brownian motions. I will not give the details of that. And then using as underlying probability space the canonical space associated with this sequence of Brownian motions, we define for each h in ht this shift. Okay, and this is a Cameron-Martin transformation, and therefore absolutely continuous with respect to the law of the underlying sequence of Brownian motions. Okay, so this is the setting. So now, as you have seen, I have to prove two convergences. So let's put that in a little bit more general setting in order not to prove the two convergences separately, but do that in one single step. So the idea is as follows. So it's very simple. So instead of considering the wave equation, I modify this wave equation, introducing here a new coefficient, say b, and adding this term. Okay, and then I consider a sequence of approximations. And what I do here, as you see, is well, I forget about b, so I only consider a. So this is the same as here. Okay, the stochastic integral. And then for b, instead of considering an integral with respect to the driving noise, I consider an integral with respect to the approximations. Okay, and otherwise I leave the other terms similarly. Okay, so this is the d and this is the b. And then the objective is to prove that actually for a choice of the parameter zeta 1 that appeared in the definition of the approximations of the noise, we are able to prove convergence in probability with respect to the Hölder norm of the sequence xn to x. Okay, so this this sequence converges to x to x in the appropriate norm. And what happens, and this is very easy to see, is that with an appropriate choice of the coefficients, we have the two convergences that are needed to prove both inclusions of the support. Okay? So then, so the objective is to prove this convergence here. Okay. This will give me the result on the support. So now, what is the method to prove that? So we have to deal with the Hölder norm, but in probability. So the idea that was already proved in a paper joined with an E for the two-dimension wave equation is instead of proving convergence in probability, let's prove a convergence in a local convergence in LP. Okay, so this is what is said in this line here, and the localization is such that in fact, so these sets L and T, whatever this is, I will give some details after that, satisfy this property. So when n tends to infinity, Ln converges to omega. Okay, so then this clearly, if we have such convergence here, so then of course we'll have this convergence in probability here. Okay. So now, how we choose this localization? So how it is possible to prove this convergence? So the idea is to choose this localization in such a way that we have control of the approximations of the Brownian motion. So this is the idea. So don't read the details because it's late and you are very tired, but the idea is that this localization keeps control of the blocks that are defining the approximations of the Brownian motion. Okay, and then as you see here, I have another parameter which appears in order to have that this sequence converges in probability to omega, so well, the probability of the complementaries converge to 0. So then we need some link between the two parameters, zeta 1 and zeta 2, and this is why here in this theorem you get we have this restriction on zeta 1. Okay. Okay. So these are some technical details, but now let's concentrate on the ideas for the proof of this result. Okay. So this is a local LP convergence. So there are two ingredients for that. So one ingredient is to have some control of the increments of x in t and in x, okay, which is related with the Hölder norm. And well, what is important here is that we need that we need so this control to be uniformly n. Okay, and then the second ingredient. So this is with the localization. Okay, and again with the localization, assume that we can prove point-wise convergence. Then it's not difficult to prove by same arguments as in the proof of the Garcia-Rodemich-Reinsel lemma that these two ingredients here actually imply this convergence here. Okay, this also was used in other papers by with Ani and with Vlad. Okay, so these are the two ingredients. So now let me give some comments on the proof. So let's concentrate on the increments in a space. Okay, so I am concentrating on this part, which is the most difficult part. So this is quite easy, so to say, but this is pretty difficult. So I will give some ideas on how to prove this upper bound, but assuming that t is equal to t bar. Okay, just one case. So let's fix t, and let's consider x and x bar, and let's consider so this term that we would like to have less or equal than some constant uniformly in n, x minus x bar to the power rho, with a rho which is less or equal strictly less than 2 minus beta over 2, and beta is the order of the Riesz kernel. So this is what we would like to have. Okay, And then what we get actually is the following. So I will explain a little bit why. So let's call all these terms by phi. Okay. So working with the terms, as you shall see, more or less, we get an inequality of this type. Okay. So then, if you look at that, so there are several things that need an explanation here. So the first one is, what is this Fn? So this Fn is a sequence, a precise, explicit sequence. So I can give you the specific the expression of this sequence, which converges to 0. Okay, and well, I have the speed of convergence of that. And this Fn comes from the following. So let's have a look on that. So we have to deal with these differences. Okay. So then, if you look at the if we come back to the equations, I should focus on xn. Okay, and consider increments in x. So that means that, well, I will divide. I will separate terms. So here I will have increment in x. Here increment in x is this dot, which is integrated, increment in x, which is integrated, sorry, this is increment in x, and here also increment in x. Okay? So then what happens is the following. So this term here is pretty difficult to study. So what we do is we modify this term in such a way that it becomes a stochastic integral. Okay? And then I have to control the rest. Right? So, and then what the rest, actually, the control of the rest is so the contribution of the control of the rest is exactly this sequence Fn. Okay? So this is where it comes from. So then you see other terms appear here. And what is quite, I would say, well, a little bit disturbing is that we would like to have an exponent here which is rho less than 2 minus beta, because you already have the over 2. But here actually we have this alpha 2, which is fine, but you have this alpha 1, which is not fine because it doesn't go until 2 minus beta, but until 2 minus beta infimum 1. Okay? So this is quite disturbing. And another thing that is quite disturbing here is that, well, here you have the same phi n, but here you have the square root of phi n. Okay? So somehow this is a sort of Gromwall structure, right? But, well, you have this trouble here, and moreover here you don't have the same exponents. But there are many Gromwall's lemma, and actually using one version of this Gromwall lemma, so I will not now go into the details of that, but you can, for example, this is a very good reference. Okay, so we are in a situation like that with p bar equal to 1 over 2. Okay, and then because you see that now with this Gromwall lemma here, so the right hand side is raised to the power 1 over q bar, and q bar is equal to 1/2. So this is the reason why here, after the application of the lemma, we can remove this 1. Okay? So this is quite magic. But anyway, it works. So now let me explain a little bit also why we obtain the 1 over 2 and where the increments on x minus x bar came from. Okay? So as I have said, for the term with approximations, I transform in a stochastic integral plus something that gives the sequence Fn. So let's concentrate on the stochastic integral because, well, I will only do one, but second one will be more or less the same. So then, one of the stochastic, the first stochastic integral, so remember, is increment in x of the Green function, and then here you have the nonlinear coefficient of the equation with the localization. Okay, so let's put a name and give a name z to this term. Okay, so this is what we have to control, to upper bound. So we just apply Hölder's inequality, okay, with the calculus of this stochastic integral, and we get that. Okay, and now since we are using Riesz kernels, okay, so the spectral density, the covariance density is given by a Riesz kernel. Using techniques of harmonic analysis, there is this formula here. So that means this expression has a spectral expression, okay? But it can be written easily in that way, okay? So then once you have this form here, so I put a star because it's not obvious, but it's a result. So once you have this result here, the idea is the following. So here you have the difference of two measures. So what to do with that? Okay. So the idea that was already used in our joint paper with Robert, the one in Memoirs, is to bound these increments here. So we have two increments here, one and here the other one. So you bound these increments to increments of the remaining terms, f, zn, zn. Okay? So since you have to bound two increments, you will end up with the sum of the following terms. So here there are change of variables and rearrangement of terms involved. Okay? But the idea is that. So in one case we'll keep f as it is, and we'll have two increments of z. In another case will be an increment of f, no increment here, but one increment here, and the symmetric one. Okay? And then a last term will be, so we keep zn, and we have a double integral of f. Okay? And now what happens is the following. So the Fn is the correction, as I said. So the term consisting of the double increment of f, when you integrate that against the fundamental solution of the wave equation, because you see that here there is sort of density of measure. Okay, so you have that and multiply by that. Okay, so then this you can have a control of that in terms of the increment x minus x bar, and actually the right exponent is that when alpha 2 is so alpha 2 where it's before, so alpha 2 is in this interval. Okay. So then in this case, when you have two increments of Zn, so then this gives you the right term. So using Lipschitz and so on, so you obtain the same as here, but you obtain the same but shifted. But thanks to a stationarity, actually you obtain the same. So stationarity is also used here. Okay, and then the remaining term is one increment in Zn and an increment in f. So one increment in Zn, here you had two increments, you got phi. So here you only have one, so you have the square root of phi. Okay, and then the increment of f integrated with respect to g gives you this exponent. So this is why you obtain this scheme here. Okay, and then thanks to this unusual Grunwald's lemma, you can conclude as far as the increments of x is concerned. Okay, so this is a rough idea of the proof. So now, in the case where the initial conditions don't vanish, in principle we could start doing the same approach. But the approach collapses because here we don't get that. We get so the same as here, but shifted, and then we cannot apply sort of Grunwald's lemma. So here, for non-vanishing initial conditions, we have just finished the proof. So this was finished last week. So it was a little bit premature to talk on this case here, but the method relies on the analysis of fractional Sobolev norms, like we use for the study of Hölder continuity of the solution. So it's much more complicated, although some basic lemmas on the behavior of measures that appear here are also used in this more general case. So if we compare with our paper with Annie, which was on the case d equal to 2, so we see that in fact the approach, well, it's similar in the same that the method is similar. So this is exactly so the same method, but the difficulties we encounter are of different type. So for d equal to 2, this is a function actually. It's not a measure, but it's a function. And then with Annie, what we did is a precise study of integrals involving these increments. So this can be done by hand, so to say. Okay, but here it's not possible because you have an increment of the measure. So then we overcome this lemma by bouncing increments, as we did in the memoirs. Another difference is that the approximation in this case of the stochastic integral by the smooth stochastic integral appears to be much more difficult. This is natural because now the problem is much more degenerate. So this is the reason. And here the idea was to combine. So this it's a sort of trade-off with the degree of smoothness of the approximation of the noise and the type of localization we are using. So this is, I will end up with the references. Okay, so you can download this article. So this is for vanishing initial conditions. So it's on archive, and then the basic references for the work have been that ones, or are that ones. Okay, thank you very much.
I have a question. You impose that your initial conditions are 0 in what you presented, and nevertheless you claim that your support theorem on some time interval which was bounded away from 0.
Sorry?
You stated your support theorem, if I'm not confused, on some interval t0, capital T cross y.
Yeah. Yeah. So this is. So we had to restrict ourselves to a time interval which is away from 0, and this is in order to get rid of this Fn here. So this tends to 0, and the way to get rid of that is just to take t. Well, it's technical, but this is the reason.
Even if the initial conditions.
We thought how to overcome this problem, but we didn't make it. So.
The time regularity, or time and space regularity, you have even in the first result with Robert, the same for time and the same for x.
Yes.
Is it how it should be, or?
Yeah. This is how it should be. Yeah. For waves, this is how it should be. Yeah.
Other questions? Your skeleton approximation is a somewhat complicated family because you have to identify all the elements, first of all, of script A, which is a very large set. So I'm wondering if you wanted to know that a particular function was in the closure of that set, would that be easy to determine or not?
Well, yeah, this is a good question. So normally this is related with the degeneracy of sigma. But yeah, you are right. So it's a characterization. But this is also what happens with the diffusions. I mean, the result of Stuck and Baladine, it's of the same type.
Other questions?
So, for the case one, spatial domain is R1. Yes, the wave equation.
Spatial.
Yeah,
Yes.
spatial domain is R1 instead of R3.
Instead of?
Yeah, one-dimensional wave equation. Sorry. How about the result on the one-dimensional wave equation?
Well, yeah, you are perfectly right. So in dimension 1, so then for the wave equation, the problem is that you have different choices for the noise. So in dimension greater than 2, since we are interested in random field solutions, we always put some noise which is correlated, because otherwise we don't have a random field solution. Okay, and then this is why we start d equal to 2 or d greater than 2. So in dimension 1 you have several possibilities. The rough possibility is to put space-time wide noise. And as far as I know, nobody has written the support theorem in dimension 1, because somehow it's the easy case. Okay, but sometimes it's also nice to start with this case. So you can write it if you wish. This is a problem, and you can do that. You can do that in two different cases. The method will be the same, but the proofs will be different. One is space-time wide noise, using, for example, the formulation of the equation in terms of a two-parameter E2 equation. So this would be an approach. And a second possibility is to consider a noise as I did here. I must say that, for example, for the Hölder continuity and also for the support theorem, we are able to consider more general covariances that I have put here. So Dries kernels multiplied by functions which are regular. Okay, but well, I have chosen this presentation because it's easier.
Other questions? Thank you.
I'm puzzled, a little bit puzzled. This is not a very question. Because when we smooth out the noise, we do the approximation, we end up normally with the Stochastic. But for the
this is so.
if you have a space-time wide noise, the Stochastic integer does not exist. So what happens?
But the problem is that here the noise is correlated, and this is what makes things work better, because the noise is smoother. This is the explanation. I have posed myself this question one time ago.
Other questions? Yes.
I wonder, how do the initial conditions influence the support?
Sorry?
How do the initial conditions influence the support?
They influence the support in the description, because then the skeleton, of course, should include these initial conditions. Okay, so this is the way. They influence in several, at least in two ways. So first, you have to put the right conditions on the initial conditions in order to get your solution and the solution of the skeleton in the space of Hölder continuous functions. But this is not, this is what we did with Robert. So we have conditions for that. Okay, so this is one way. And the second way is in the definition of the support, in the definition of the skeleton. So here, in this equation, you have to add the two terms, which are of this form, same terms.
So what is the regularity of these initial conditions, so that
These initial conditions, there are several possibilities. But roughly speaking, they should be differentiable, and then and the derivative should have some Hölder continuity property.
So there must be better regularity of the input.
Yeah.
Other questions? No? Let me thank you again.